Class. Now we are going to derive an expression for the pressure of ideal gas which they are exerted on the walls of the container in which it is being enclosed. So to derive the expression for the pressure, we assume that there are n number of molecules that are being enclosed in a cubical box of length L. As you can see in this diagram over here, there is a box in which n number of gas molecules are being enclosed. Then further we assume that the masses of each gas molecules equal to m. So total mass of the gas molecule will become the multiplication of number of gas molecule into mass of each molecule, and that's will be equal to n into small m. As it's a cubical container, so the area of each of the wall is going to be equal to square of the side of the cubical box. So it is going to be equal to L square, and the volume of the cubical container will be L cube. Density of gas, as you know, mass upon volume. So density of gas will become N into small m upon L cube. That's our consideration which we are making before deriving the expression for the pressure. Now guys, now class, as we have said that there are n number of molecules, they are randomly moving in this cubical box in all possible direction with all possible speed. But in our case, we are deriving the expression for the pressure. So we will assume any particular a typical molecule of the gas, a single molecule of gas, which is moving randomly in this box. And we further assume that this molecule is not colliding with the any other molecule, rather it is colliding with the only walls of the container. Now you might be thinking, how is it possible? It is possible as we have done the previous numerical, and there we have seen that the free path, mean free path, while solving the numericals, we were having the equation lambda equals to, the lambda equals to 1 upon 2 pi d square under root 2 pi d square into n upon v, and then we replaced n upon v with the T upon kBT. And when we replace this equation, we got lambda equals to kBT upon under root 2 pi d square into P. So this equation tells us, this particular equation tells us that when we will reduce the pressure, the mean free path will increase. And we know mean free path is nothing but the path between the two successive collisions. So by reducing the pressure, we can adjust the mean free path. So we can control the, now we can reduce the number of collision between the molecules by adjusting the pressure, and that's we have done over here, that we have adjusted the pressure in this particular case such that these molecules are not colliding with each other, rather they are colliding with the walls of the container. Now we further assume that, as we have discussed in our previous classes, that these gas molecules are now moving in all possible direction with all possible speed. So let's say the speed of this particular molecule is nothing but equal to v. So this gas molecule is having the speed v in our case. This is moving with the speed v. And the component of v along the x, y, and z axes are vx, vy, and vz. Vx, vy, and vz. This is vy. This is vz. These are the components. We further say that, let's say this particular molecule is colliding with this wall, which we have set it over here. So this molecule is going to collide with the wall. While saying that, let's say if this molecule is going to collide with the wall with the speed v, during that process, as you can see, since the molecule is moving along the x-axis, there will be no change in the y component and the z component. So vy and vz, they are going to be unchanged. Now, what is going to be happen with the vx? Will there be any change in the magnitude? The answer is no. As we have discussed, in the assumption that between the two successive collision, the molecule is moving with the constant speed, constant velocity. So there will be no change in the magnitude of Vx. So M is going to move with the velocity Vx, and it is going to collide with this surface area A1. Okay. Now what will happen after collision? So again, remember the assumption. We have said that these each and every collision, whether the molecules are colliding with each other or the molecules are colliding with the walls of the container, the collision is always going to be elastic. Once we say the collision is going to be elastic, that means there is no loss of energy. So means what? That means after collision, this molecule will get reverse in their direction, and it will move in the opposite direction with the same magnitude. So what will get changed? They will get change in the momentum. So we can say that the initial momentum of this gas molecule before colliding with the wall, that is going to be m into Vx, and the final momentum will be m into minus Vx, because here direction is getting reverse. So momentum will become minus Vx. So minus m into Vx. So initial momentum mvx, final momentum minus mvx. So what will be change in momentum then? So the change in momentum is going to be final momentum minus initial momentum, and so it is going to be minus mvx minus of mvx. So it is going to be minus of twice of mvx. This is the momentum, change in momentum of the molecule, gas molecule. As a result, since momentum minus sign indicates the gas molecule is losing the momentum, okay? Minus sign indicates there is a lose in the momentum of the gas molecule. As a result, someone is losing, someone will gain. Which one will gain? The particle with which the gas molecule has been collided, and it has collided with the wall. So this wall will gain the collision of 2mvx. So the momentum transfer to the wall during collision is going to be 2mvx. That's the momentum gained by the wall of the container. Now further think, with our motto is to find the pressure. To find out the pressure, pressure is nothing but force upon area, and force is rate of change of momentum with respect to time, dividing with the time. So we have got the momentum over here. Now we have to find the time. Which time? Time interval between the two successive collision. Now again see, this gas molecule is moving with the speed. This gas molecule is moving with in one direction and colliding with the wall A1, colliding with the wall A1. colliding with the wall A1 over here, the direction is getting reverse. Direction is getting reverse. It will again travel towards A2. Further, will get collide with the A2. Direction will get reverse and come towards A1. So the path distance traveled by the gas molecule between the two successive collision. So from A1 to A2 and A2 to A1. So molecule is moving after colliding with the A1, it is going to A2, and then after colliding with the A2, it is coming towards A1. So the total distance travel between the two successive collision is equal to 2L. What is the speed? Speed is Vx. So the time duration between two successive collision, it is a distance upon time. So the time duration between the two successive collision is going to be 2L upon Vx, distance upon time. So we have the change in momentum, we have the time. So we can calculate the force over here. Now here we are considering a single molecule, only single molecule. Okay, so we can find out the force because of this single molecule by putting the suffix 1 over here. 1 means we are taking the only single molecule because of molecule 1. So average force because of molecule 1 on this wall which we have selected is going to be the momentum upon time, and as you can see over here, momentum is 2m Vx1 upon 2L upon Vx1. While solving that, 2 will get cancelled out, and we are going to have the answer average force because of molecule 1, that's equals to mVx1 square dividing with the L. Similarly, the single molecule exerting this one force. If you take second molecule, because of second molecule, the force will be mv square x2 upon L. Because of third, mv square x3 dividing by the L. So only the suffix 1 will get changed. 1 will become 2, then 3, then n. And for the nth molecule, it will be mv square xn dividing with the L. Okay, so in that way, all the rest of molecule, all the n molecule, they will apply the force on this wall. They will apply the force on this wall. So now we will find out the average force because of all the molecules. So to finding out the average force, what we have to do, we have to add up all the forces because that's a total force is going to be applied by all the molecules. Then they are moving in the same direction at the same time. So total force because of n molecules is going to be addition of all, and then we will add all. So it is going to be, as I said, it is going to be mvx1 square upon L plus mvx2 square upon L plus mvx3 square upon L, and till that we are going to have mvxn square upon L. That's because of nth molecule. In all, we can have that this is our total force. This is our total force. Okay, this is our total force. So in that, what we have common? We have the common term m by L. So we take m by L common, and so total average force because of n molecule on that sided wall is going to be m by L Vx1 square plus Vx2 square plus Vx3 square till we are going to have the Vxn square. This is the force. Now we know what is pressure. Pressure is, we have to find the expression for pressure. What is pressure? We got the force, and all the n molecules, they are applying the force that is equals to that. This is equation number 1. So to find the pressure is going to be force upon area, the area of the wall in which all the molecules are applying the force. So the pressure will be, we have the force dividing with the area, and we know the area of the wall was nothing but equal to L square. So the pressure will become mvx1 square plus vx2 square plus vx3 square dividing with the L. This is our force. Further dividing with the L square, and thus pressure will become this whole term dividing with the L cube. But you know what is L cube? L cube is nothing but equal to volume of the container in which gas has been enclosed. So P is going to be mvx1 square plus vx2 square plus vx3 square till vx1 square dividing with the capital V, which is nothing but the volume of the container. Now class, what is Vx1? Vx1 is nothing but the speed of the molecule 1. What is Vx2? Speed of molecule 2. So in this container, we have the n molecules. This molecule is traveling with the speed of Vx1. This molecule is traveling with the speed of Vx2, then Vx3, Vxn. If we have to find out the average of all these speed, all this velocity, so we can find out the mean of the square of all the speed, and that is going to be given by this particular formula, which is Vx square. Of course, since we are finding the average of all the x component of the speed, so Vx square is going to be Vxn square, adding up the square of all the x component of n molecules, dividing with the number of molecules. And from here, we will get therefore n into Vx square will be this whole term Vx1 square plus Vx2 square plus Vx3 square till Vxn square. That means in this particular expression of pressure, which is our equation number 2, we can replace this whole bracket. We can replace this whole bracket with the term n into Vx square. Okay, so from equation number 2 and equation number 3, we can say that P is going to be equal to m into n. This whole term bracket is going to be replaced by n into Vx square. So m into n Vx square dividing with the volume of the container. And this is our equation number 4. Okay. Now class, here the pressure which is exerted on the particular wall, that is in x direction. If we assume all the things which we have done till now, if we have, instead of taking the x direction, if we would have taken in the y direction, then the pressure in the y direction would have been m into n into Vy square dividing with the m. Instead of adding Vx, it would have been the Vy. So this is my Px, this is my Py. Similarly, we can write Pz, and that is going to be m into n Vz square dividing with the n. Okay, so along the x direction, the pressure exerted by all the gas molecule on that particular wall. Along y direction, along z direction. So what we can say that, what we can conclude that since in an equilibrium condition, remember in equilibrium condition, it is nothing like that the gas molecules are exerting the different amount of pressure on the different wall. That is nothing going to be happen. If that would have been the case, the chamber would have been the unstable. So in equilibrium condition, the pressure exerted by the gas in either in x direction or in y direction or in z direction, it is always same. That means when we say it is same, we know it is m and v are going to be the same. That means Vx square, Vy square, and Vz square, they are same. The square of the component of x, square of the component of y, the velocity, the component of velocity of y component of velocity, and the square of the component of velocity, the z direction. They're always going to be same, and that is being called as a symmetrical condition. Okay, so in symmetry, in general, in symmetry, we say that which we have discussed in our previous slide, we say that v square is nothing but equal to vx square plus vy square and vz square. How this term is going to be happen? We know that what is v? V bar is nothing but vx bar plus vy bar plus vz bar. That is going to be, because as you can see in vector, This was the V. This is V. This is Vx. This is Vy, and this is Vz. So in vector form, we can write V is nothing but Vx bar plus Vy bar plus Vz bar. So in magnitude form, of course, we can write V square equals to Vx square plus Vy square plus Vz square. This is, of course, in vector you must have learnt. Okay, square of any vector is nothing but the scalar. So even if I'm putting the bar over here, it is nothing but a scalar term. The square of any vector is nothing but the scalar term. So v square is nothing but equal to vx square plus vy square plus vz square. And by symmetric, as we have discussed, all these terms are going to be the same. And that is equals to, if I will substitute this value in this equation over here, what we are going to get? It will be 1 by 3v square. How come? Just replaced. If I will substitute all the similar value over here, we are going to have v square equals to this. If I replace vy with the vx, vz with the vx, all terms will become same. So 3 times vx square, and therefore vx square is going to be 1 by 3 v square. Okay, so vx square, vy square, and vz square all are same, and that's equal to 1 by 3 the square of v bar. Substituting this value in the previous equation, where we had p equals to 1 by 3 n upon v into m vx square. This vx square we are replacing with the 1 by 3 v square. Okay, and so we have equation this one. Now what is n upon v? Remember, what is n into m? In our consideration, we said that n into m is nothing but the mass of the gas. We can replace n into m as a capital M. And what is m upon v? Density. So even we can express the pressure in terms of the density of the gas molecule. So it all depends upon what sort of data they have given in the numerical. If they have given you the number of molecule, if they have given you the mass, total mass of the gas molecule, or they have given you density. Accordingly, you will select the formula, the form of this expression for the pressure. In this whole expression class, we assume that there is no collision between the two molecules. But even if we consider that the molecules are going to be collide with each other, okay, even if we consider that the molecules are going to be collide with each other, in that case, what will happen? What will happen? Here, if we are considering that we are having an enclosed chamber in which the molecules are colliding with each other, if such conditions are going to be happen, so what will happen? Because of the collision, some molecules will gain the velocity, whereas someone else will adjust that velocity. So even if we consider the case that the molecules are colliding with each other, there will be no change in the expression for the pressure which we have derived over here. Okay, there will be no change. So this is the expression for the pressure which was supposed to do. I hope you must have understood the basic idea behind it. Remember, while finding out the pressure, we have to first calculate the change in momentum. Next, the force exerted by the gas molecule on the walls of the container, and then the pressure, momentum, force, and pressure. That's a key point which you need to remember, that you can easily remember this lengthy expression. So this much only for today. I hope you must have understood the concept, and in case if you will be having any problem, you can write your doubts in the comment. We'll definitely solve these doubts in our next session if there will be. Thanks for watching. Thank you.